is the outline that I will follow. First, I will talk about the observation of resistive switching, especially in transition metal oxides, three-dimensional characterization of materials, ionic liquid characterization combined with conductive AFM, which is a very interesting method I learned at Stanford, in-situ electrical characterization using the conductive AFM inside the TEM or inside the SEM, also characterization of two-dimensional materials, and finally one prototype that I fabricated with graphene to protect some AFM probes. So basically what we are doing when we are using conductive atomic force microscopy is we have a very sharp tip at the end of a cantilever that we can scan over the surface of a material. Normally it's a ultra thin dielectric. And using this technique, we can apply a potential difference between the tip and the substrate, and we can measure the current across the oxide. When there is a defect inside the oxide, we can see that the current signal can change. And using this technique, we can get topographic and current maps of any material with nanoscale resolution. Normally, I use this technique in my studies to analyze resistive switching. Resistive switching is basically a property of some insulators that can cyclically change their resistance by producing local difference. Here you can see one metallic tip, one metallic substrate, one insulator in the middle, and when we apply bipolar electrical stresses, we can form a conductive nanofilament and destroy it across the dielectric. With these two states, we can emulate the ones and zeros of the binary code and use this material to fabricate logic memories, which are called resistive switching memories. With this technique, I use it to analyze the structure of some polycrystalline transition metal oxides like hafnium oxide, and I observed that the resistive switching only takes place at the grain boundary of the polycrystalline materials, which is something that was unknown before we did this work in 2012. In order to observe this performance, I needed to modify the standard conductive atomic force microscope, because one standard conductive atomic force microscope cannot measure bipolar currents, because if we measure in air environment, normally we could induce local anodic oxidation if we inject electrons from the tip. So basically you can only measure currents in one polarity, and because the linear preamplifier and the electronics of the conductive AFM are limited, we normally can apply only voltages from 0 to 10 volts and measure currents up to 1 nanoamp. In order to solve these limitations, what I did in my previous work was to try to solve these problems. First, I measure in a vacuum environment, which means that I can have both polarities. And then the problem of the current and voltage ranges, I solve it by connecting one semiconductor parameter analyzer directly to the tip of the conductive AFM. And using this setup, I could apply voltages from minus 20 volts to plus 20 volts, and also measure currents from 0.1 picoamp to 1 milliamp. Actually, I also could apply a current limitation that you can see here, because the resistive switching normally requires a current limitation to avoid the lateral expansion of the conductive filament. So using this setup, we were the first people to analyze in situ resistive switching, and actually this setup was later adopted by many other scientists, including some friends at the University of Manchester. But this setup has one problem, which is if we want to do lateral scans, this is a little bit more challenging. This setup that I have shown here is only valid for spectroscopic measurements where the tip is static in one point. The reason is that synchronizing the movement of the tip with the electronics of the semiconductor parameter analyzer is quite complex. So in our next work, what we did is we use the standard AFM, but we replace the linear preamplifier by a logarithmic preamplifier, which allows us to construct current maps in which the current scale expands several orders of magnitude, which is the first time we did this in 2000. Actually, it was done in 2006. We published in 2008, and later some companies like Etching, like Park Systems, have adopted this setup. Because here we are talking about conductive filaments, Normally, these conductive filaments are produced in metal oxide metal devices at the device level. However, we don't know how many conductive filaments are being formed, what is the size of this conductive filament, etc. So in order to analyze this, what I did in one of my previous papers was to induce the filaments at the device level, etch the top electrode, and then scan with the tip of the conductive FFM. And this allows us to make some statistics about the size and the currents driven by these conductive filaments. However, well, actually, this can be also done to analyze the degradation of other types of devices, like, for example, field effect transistors. In this case, in this paper, we have different field effect transistors. In this case, we have 3. We have stress, 2 of them, one by NBTI and the other one by channel hot carriers. And after that, we remove the gate, and then we scale the surface of the dielectric using the tip of the conductive FM, and we can see the appearance of conductive spots related to the degradation based on the stress, because the fresh devices, they don't show this type of highly conductive areas. So in both cases, there is one compromise, which is the etching needs to be really, really good, otherwise we will be damaging the oxide. So here we wanted to try to explore other methods to etch this top electrode. One of the methods is just to use the tip of the conductive AFM. If we apply high force, then we can etch this metallic electrode. And using this approach, some scientists have managed to have these metal insulator metal structures, induce the conductive nanofilaments, and then analyze the size and the current driven by these filaments when the samples are in high resistive state and in low resistive state, and also in the fresh state. Here you can see in this article, the authors analyze these 3 samples, and it is very clear that the sample in low resistive state after the set process shows filaments that are much wider and they drive higher current. And actually, one can also do an additional experiment, which is not only to etch the top electrode, but also to etch the dielectric where the filament is contained. So this can be done basically by applying high mechanical stress, high contact force. In these papers, the authors etch progressively this dielectric containing the conductive filament, and this allowed them to make one 3-dimensional map of this conductive filament. So by using this approach, the authors observed that the top diameter is wider than the bottom diameter, which means that the filament has a conical shape with the narrower end at the bottom. However, we have also repeated these experiments. We want to warn the authors working on conductive FM that they need to be careful. Depending on how you do the etch, you can damage the material. You can change the properties of this material, because it could be possible that the phase of the material changes. For example, in this case here, you can see in the top row one piece of silicon. When we etch, and then when we etch the center for a couple of nanometers, what we observe is that the central area is much more insulating than all the others. So basically, we have changed the resistance of this piece of silicon by applying high mechanical force. Actually, this is also something we are observing in other materials. And actually, we have analyzed the etch region by cross-sectional TEM, and we can observe very clearly that inside the etch regions, we can observe some dark particles that are not present outside the etch regions, which means that the tip pressure has induced these particles. And these particles we have analyzed with higher resolution. We observe that they are related to phase change in this dielectric, and also in some cases even there is migration of metallic atoms from the electrodes inside the dielectric, because they acquire a lot of energy when we are applying high pressure with the CAFM. Actually, this has been also corroborated using theoretical simulations. These materials can change the phase based on the pressure. So in order to solve this problem, the problem of etching the top electrode, we have developed, together with our friends at Stanford University, one setup that consists on using one liquid top electrode. We designed this sample, which consists basically, we have the dielectric on a metallic substrate, and instead of placing one solid metallic electrode, what we have done is to deposit a very thick photoresist, open a window, and deposit 2 contacts on top of the photoresist. Then we put a drop of an ionic liquid that is conductive, and then we polarize the structure between the top gate and the sample holder. And what we can do is to apply these electrical stresses, and the ionic liquid is conductive. This stress that we apply to the top gate will be transported to the window, and the dielectric will be stressed. The good point of this is that after the stress, I can rinse my ionic liquid, and I can scan this exposed area of the dielectric using any technique, not only conductive FM, but also SEM and nanosims and EDX and any other technique. So this test structure is easy to fabricate. If anybody is interested, can read our paper in Proceedings of IPFA conference, but you can also send me an email and we will be happy to fabricate these kind of structures for you. So here I show you one example of what you can do with this structure. For example, we have analyzed titanium oxide using 2 different kinds of ionic liquids. One is not very conductive, which is this ionic liquid called DEMEBF4, and another one that is more conductive that I will talk later. When we do these stresses with different polarities, we can observe that the samples show resistive switching very clearly. We can increase the conductivity, and when we apply minus 5 volts, we can come back to the initial state. We also observe that different sizes for these windows result in different current levels for both high resistive state and low resistive state, indicating that this is a distributed phenomenon. Thanks to the conductive AFM and to this ionic liquid method, we have analyzed the fresh sample, and after the first set, after the first reset, after the second set, and we observe very clearly that after the set processes, the number of conductive spots is much higher, and the currents driven by them is also much higher, confirming that this is a distributed effect. And actually, it can also be observed if we make statistics of the maximum current for the fresh set reset fresh sample. We observe that the current initially is slow, then increases, decreases, and increases again, confirming the presence of resistive switching in a distributed manner. Actually, because the surface of the material is exposed, we have also analyzed the surface of this material with nanosims for different stress times, and we have observed very clearly that as the stress proceeds, the amount of oxygen on the surface is higher, indicating that the resistive switching is driven by the movement of oxygen ions towards the surface of this material. In the next example, we have used a much more conductive ionic liquid, which is called KNO3, and in this case, we observe no area dependence in the low resistive state. This is indicating that the current in low resistive state is a local phenomenon driven by a single conductive nanofilament. So thanks to the conductive FM, we can scan the whole area of this window, and we observe that there is only one location showing currents that are much higher than the others observed in the image. Actually, the obtention of this current map was very difficult because this nanofilament has a diameter of 4 nanometers and the window is 20 micrometers. So in order to get this image, we had to scan the sample with a resolution of 1024 pixels by 1024 lines, which reduces a lot the scan time. This scan that you see here took us more than 1 hour for one scan. However, this improved the lateral resolution, and we could successfully observe this conductive spot. Okay, in the next section, I want to talk about in-situ electrical characterization. Combining the conductive AFM with techniques like SEM and TM is very beneficial because you can observe in situ the movement of these electrical charges. Actually, this has been used by other people in the field of resistive switching devices. What we have done in our laboratory is we have implemented one conductive atomic force microscope inside one scanning electron microscope. Here you can see the SEM image of the tip inside the machine. And we have prepared a sample consisting of zinc oxide nanowires. So basically what we have here is one tip touching the nanowire, and you are watching in situ how these nanowires bend using the camera of the SEM. So here in this video, in this image, I show one image of the tip of the conductive FM touching this nanowire, and actually you can keep your tip static on one nanowire and apply different stresses and observe how this nanowire starts to bend. Actually, this is a video, but here I cannot show you the video in this presentation. But basically, here I have captured some images at different times of the video, and basically we could observe when the currents are being generated. The zinc oxide nanowires produce current when they are bent, and according to the paper reported in Science in 2006 by Professor Chonli Wan, this nanowire is related to piezo-electricity. However, using this setup, we have observed that the current not only appears when the nanowire bends, but also there is a peak of current when the tip enters in contact, and another current when the tips start to slide laterally, indicating that there is current produced by the contact potential difference and by triboelectric effects, not only piezoelectricity. This has been only possible to be demonstrated thanks to the combination of these two techniques. In the next section, I wanted to present some results on two-dimensional materials characterization using conductive atomic force microscopy. In this field, I started to work in 2010. First, I used a scanning electron microscope to analyze things like the grain boundaries of the substrate that induce corrugations in the 2D material, multi-layer islands in the 3D material, wrinkles in the 2D material. And actually, I analyzed this with the conductive FM. I could quantify what is the height and what is the width of the wrinkles. We developed one method to reduce the amount of wrinkles by increasing the roughness of the substrate. And we also analyzed local defects of this material using scanning tunneling microscopy and some atomistic simulation. And also we analyzed the density of defects when these 2D materials, in this case graphene, is exposed to oxidative environments. Actually, we observed that at the grain boundaries, there is space for oxygen bonding and the 2D material can degrade. Later, it was demonstrated that in molybdenum disulfide, piezoelectricity can be produced by applying mechanical strain. This has been demonstrated at the device level by Professor Chonli Wan in Nature. And in this video, you can see how one two-dimensional material can bend when it is exposed to mechanical stresses. So, what we did in our laboratory is to try to do all this work at the nanoscale using a piezoelectric ink of molybdenum disulfide. We fabricated the ink by liquid phase exfoliation, and then we deposit this ink on a substrate that contains several holes, so that the molybdenum disulfide gets suspended on these holes. And then we apply mechanical stresses with the tip of the conductive atomic force microscope, and at the same time we collected the currents produced by this material. And we observed very, very clearly that when we increase the contact force, the current area and the current volume increases in this sample, confirming that the current is produced by the mechanical stress. Finally, I would like to introduce some work that we have done related to the use of graphene to coat AFM probes. Basically, one AFM probe looks like this. Is very sharp and is made of silicon coated with a thin varnish of metal, normally platinum, like 10 nanometer platinum. However, this kind of tips can degrade very fast, and what we try to do is to extend their lifetime by coating them with liquid phase exfoliated graphene. First, we observe that the coating doesn't alter the mechanical properties of the cantilever, and therefore these tips conserve these properties, which is something that we want. Then we have compared the lifetime of the standard tips, which are uncoated, just adhesive, and graphene coated tips. And what we observe is that for the standard tips, we have that the first scan shows very high currents, but after only 13 scans, under the same conditions, the currents start to decrease a lot. And if we apply IV curves, we can confirm that the linear conductance of these tips has been reduced and that we observe much lower currents. Actually, if we use SEM to analyze the degradation of the apex of the tips, we can observe very clearly that the metallic varnish has been melted. In some other cases, it's just that some particles has been attached, and in some other cases, basically the bulk of the tip, everything, including the silicon, has been removed. Here, in this case, the silicon is exposed because the metallic varnish has been melted. When we use the graphene coated tip, we can observe that even if we scan up to 92 times, tip still shows quite high currents, and the graphene has effectively protected this this apex of the tip, and it can conserve these electrical properties. Actually, we have repeated this experiment in multiple tips and at different locations of the sample, and we always observe that the graphene coated tips can scan a higher amount of area. This is important because doing the experiment only with one tip will not be meaningful. There is always a variability from one tip to another. And in all cases, we observe that the graphene coated tips live longer. We have also tried other experiments to also try to confirm the lifetime of the tips. And we have observed, in this case, we apply a constant voltage stress at one location of the sample with the tip static in one point. And we can observe that when we use standard tips, the current is initially very high, and after a few seconds it drops and we just observe electrical noise. For the graphene coated AFM tip, we can observe also high currents, and this current is maintained over the time and it's quite stable. It's much more stable in agreement with the previous result. Actually, the graphene coated tip seems to be as stable as the diamond tip, as durable as the diamond tip, but with the difference that the diamond tip shows more current instability, and this is probably related to the roughness of the diamond coating. So until here, this is everything I wanted to present. I think the main conclusion of my work is that the conductive CAFM is a very powerful tool to analyze the electrical and the mechanical properties of different materials at the nanoscale. Actually, it has a unique performance and it can be very useful for many different research directions. Traditionally, it has been used to analyze the reliability of ultra-thin oxides, but as you have seen in this presentation later, it can be applied to measure resistive switching, to make three-dimensional scan. It can be combined with ionic liquid, with SEM, with TEM. So it is something very attractive. I think it has a very bright future in the field of flexible electronics, because flexible electronics are also exposed to mechanical stresses. And here, finally, I just wanted to show you some of my recent works. In case you are interested in this direction, you can check here more information. That's everything from my